This topic actually stems from the idea of Faraday's law and Lenz's law. If you haven't done that already in O levels, or if you need revision, then I will suggest you go back and watch the video from the O levels course, from the O levels playlist, to revise Faraday's and Lenz's law. So today we will explore what is the magnetic flux and what is magnetic flux density. Very simple concepts in terms of visualization, and very easy to apply in questions as well. So first he says that we need to understand what is the magnetic flux, okay, and then he says that students must be familiar with this formula. Then what is magnetic flux linkage? The point number 4 and point number 5 are taken from O levels. So let's go through first 3 points in one go. Okay, so what is magnetic flux? Remember, whenever you read the word flux, it is simply going to mean number of lines. That is it. So if I say magnetic flux, I'm actually referring to the number of magnetic field lines between the North Pole or between the South Pole or around a coil that is carrying current. Okay, so magnetic flux would simply be the total number of lines. And when we involve density, that means we want a unit method that in a certain area, for example, how many number of lines exist in a certain area. Now, the unit of magnetic flux is Webers, represented as WB. So for magnetic flux density, it will be Webers per meter square. This is Webers and this is Webers per meter square. So let's see how to visualize this. So we can see that between the poles of North and South, there are many number of lines passing from one pole to another. If we were able to count all of these number of lines, then I would have calculated the number of magnetic field lines, or I would have calculated the magnetic flux, simply magnetic flux, not the density. And that in physics is represented as phi. If I wanted to calculate the magnetic flux density, if I'm looking for the density factor, that would mean that I'm looking for the number of lines per unit area. So the green area that has been highlighted over here, for the sake of example, let's visualize that this is 1 meter square area. And in that area, let's say if we count these red number of lines, let's say that there are 50 lines in that 1 meter square. So the magnetic flux density will be 50 Webers per meter square. And another unit that you're familiar with this is actually Tesla, which we did in previous videos, in which we have done F equals to ILB and F equals to QVB. In that formula, when we were looking at B was actually the magnetic flux density. Its unit was Webers per meter square, but since in those chapters, it was beyond the scope of the knowledge of that chapter, we don't discuss it over there, we discuss it over here. So magnetic flux density, we are basically talking about the letter B, if you just want to look at the formulas. So the formula actually becomes that the total number of lines, phi, magnetic flux, will be equal to the magnetic flux density, which is B, multiplied by the cross-sectional area A. So this is Webers per meter square being multiplied by meter square, of course, going to give you an answer of Webers. Webers is flux, flux is the number of lines, right? So then we move back to the syllabus and we see that we have finally understood what is phi equals to BA. We understand what is the concept of magnetic flux, and we see that it is the product of magnetic flux density, which is B, with the cross-sectional area A, which is A, and the magnetic flux phi equals to the product of this, which is what is represented over here. Now let's try to understand the word linkage. Now, whenever you see linkage in any concept, at least in magnetism, you will realize that he's going to talk about actually the number of turns of a coil. Okay, and this will be represented by a number letter N in the formula. So for example, over here I can see, just for the sake of example, if I wanted to visualize what is the magnetic flux density, what is the value of B for this area. So this B is less than this B is higher. Why? Because I can see more number of lines in that same area. So the value of the number of lines, which is phi divided by A equals to B, this formula comes from phi equals to BA. If I wanted to find B, I will take A over there. That is why we get this formula. So that is, since the area is small, or the area is similar, number of lines are higher, so the magnetic flux density will be higher. So when you count all the values, you get phi. When you want to find for a certain area, you get B. This is what the formula actually represents. Okay. Now let's talk about the linkage concept. What is linkage? Now in linkage, we simply say that if we have a coil, for example, let's say that we have a coil of n number of turns, then this phi equals to BA is actually for a single coil. We are just looking at one surface area and how many number of lines are passing through it. But if we have more number of turns, for example, 1, 2, 3, 4, 5, 6, then these number of lines actually pass through these 6 cross-sectional areas, and the effect of magnetic flux or the effect of magnetism is going to increase, right? And how much is it going to increase? It is going to increase by n times. So this is magnetic flux. If I write down magnetic flux linkage, then it will only have a factor of BA plus a new factor, which is going to compensate for the number of turns. So this becomes NBA or NAB, however you want to remember this. Okay. All right. So I hope that we don't find this difficult. If you're only finding this for certain area, for example, a cross-sectional area, then you can use this because it doesn't have number of coils. But if you're trying to find this for the number of coils, which has turns, which has multiple coils, which has links, because why are we saying that it is a linkage? Because one magnetic field or one induced magnetic field is being linked with the next one, being linked with the next one, and so on and so forth. So in a series fashion, the effect is increasing. So this many number of times the effect will increase because this many number of times the magnetic flux density had a chance to pass through a cross-section area A. Okay. All right. So we understand the word linkage in the syllabus. Now let's briefly undergo Faraday's law and Lenz's law. Now Faraday identified that the induced EMF on any system is going to be proportional to the rate of change of magnetic flux. We have understood that the magnetic flux is actually equal to BAN divided by T as usual. Sometimes it is also referred to as the gradient function, right? So this is actually referred as the gradient function. If the rate of change is higher, the induced EMF will be larger. So this was identified by Faraday, that if you try to change the magnetic field, and how can we do that in a simple laboratory experiment, that we have a coil, we have a magnet, could be a south pole, could be north pole, does not matter. If we bring it closer to the coil and if we move it away from the coil, or even so, let it be over here. As long as the magnet is moving, there will be a change in magnetic field observed by the coil, by this conductor, and that will induce an EMF in the conductor. This is what simply Faraday had discovered. What was the role of Lenz's law? But Lenz identified that there is a negative sign in the formula. There is going to be negative delta phi divided by delta T. Generally, in numerical questions, this negative is not put forward. This is only going to be used in graphical analysis. What does this negative mean? It means that if the rate of change is positive, the EMF induced will be negative. If the rate of change is negative, then this negative multiplied by this negative is going to give you an answer of positive. So what it tries to tell you is that whoever is trying to bring about this change in magnetic field, the EMF induced will be in such a way that is going to oppose the change of magnetic field, that whoever is trying to change it. So what actually happens? So if we visualize a coil, I'm going to draw the coil a bit spread out. Let's say this is an ammeter, and let's say we bring in a magnet in the coil. I've discussed this detail in the O-levels video as well, but I'm just going to briefly discuss it over here. So if I move the magnet over here, for the sake of example, let's say that the current in the coil is actually in this direction. Okay, we use the right hand grip rule. We use the grip rule, and we find out that this current actually produces a pole, north pole on this side. So when we try to bring the north pole closer, this north actually starts opposing this north. So it requires an effort if you want to keep moving this magnetic pole into the coil, you will need to put in some effort. This is not going to happen on its own. Now, interestingly, if we try to move it away, the current direction changes, and now the current is going to start flowing in this direction. And if you apply the grip rule again, it will produce a south pole over here so that it is attracted, so that the north pole cannot get away. So what is, in summary, what's actually happening? There is an effect of opposition to the external source. So if the magnet was not moving, the induced EMF would not exist. and the induced current would not exist. And if there is no current, there will be no magnetic field, and it will not be able to oppose the magnet who's trying to create it in the first place. So basically, in a very lazy man definition, we can say that this is actually like opposition to the maker. The magnet's motion actually made the current, and now the current, after being induced and after being produced, is creating such a magnetic field around itself that it is going to oppose the movement of this magnet. And it doesn't matter if you want to try this with South Pole, it will behave similarly. If you bring in the South Pole, this will make a South Pole. If you take away the South Pole, this will make a North Pole. This effect of opposition was introduced by Lenz in this equation as a negative sign. So if I write down the equation of induced EMF, that is equal to, let's say, BAN, or delta phi by delta T, this part is contributed by Faraday, and the negative part is contributed by Lenz, which makes this whole equation of induced EMF. Okay, this opposition will play a part in the graphical analysis, but not in the numerical so much. Let's try to solve a few questions. Now, over here we have to write down a simple definition. Notice the word linkage in the question. If he's talking about linkage, most definitely he's going to talk about the number of coils as well. Okay, so I'm going to type the answer over here. You can confirm this from the marking theme of the respective question as well. So he says, what is magnetic flux linkage? Now, since he's talking about flux, I am very sure that he's going to talk about, or he's going to actually refer to, phi equals to BA and N introduced in it. Now, since this is the formula, I'm going to discuss this formula in the definition, how it's going to be. So this is actually the product of magnetic flux density with the cross-sectional area passing through n number of coils. You can phrase it any way you want. What you want to do is you just want to describe the formula. All right. Okay, let's move to the question. This is a very common question in which a coil is given to you. No need to worry about this. He says that it has 160 turns. So this is our N, 7.5 millitesla. This is our B. He says this is the diameter. So we will have to look at the radius because we want to find the cross-sectional area. He says that the flux density changes or reduced from 0 or reduced to 0 in a time of 0.15. So he's asking us to find out the induced EMF. You see, the induced EMF formula was generally change of flux divided by change in time. So we have the formula for change of flux, which is NAB divided by time. Although if it was just a single coil, then N would not be present over here because then that will have a value of 1. So right now we have the value of N, 160 turns, we have 7.5. Let's put those values. So 160 as N, the cross-sectional area we'll get later. So 7.5 milli, so it's 10 raised to the power minus 3. And then let's find out the area. Since this is a circular coil, I will use the formula pi r square. This is assumed that you know this at least up to A levels. So pi into r square, which is 2.4. So I'll have to half it. So 1.2 into 10 raised to the power minus 2. Again, the values have to be converted to standard form. Pi r square divided by t, which is 0.15. When you put this all in one go, you will get your answer as 3.61 something, which is actually 3.62. So it becomes 3.6 millivolts as shown in the question. Let's move to the next part. This is where that idea actually comes handy, which we discussed that EMF is proportional to, let's say, negative of rate of change of magnetic flux. Now, why magnetic flux can also be proportional to the current as well? Because if the current is not flowing in the conductor, there will be no magnetic field. Let's see to that. So we have the formula V equals to IR, and we have the formula that EMF, which is basically voltage, is equal to rate of change of flux divided by rate of change of time. So if we place this as BAN divided by T, and since this is voltage, let's place it over here. What do we get? We get BAN divided by T equals to IR. Now, in some questions, he will talk about changing the magnetic field. He will sometimes talk about changing the flux. He will sometimes talk about changing the current. But are they related? Yes, they are related. We can see that if T, AN, and R are constant, then B is directly proportional to I. right? So if he talks about changing flux or flux density, which is per meter square, it will be linked to current. If he talks about increasing or decreasing current, he's actually talking about increasing or decreasing the flux. So whatever graph is given to you over here, we can see that the graph of flux is given to us, the flux density, which is B, which we figured out is actually proportional to the current. Okay, so let's see what's happening. We have to note that induced EMF has a formula of EMF being proportional to rate of change of phi with respect to time. If you decrease time, the EMF increases, and vice versa. So let's look at the first situation. The EMF actually changes from 7.5 to reduce the, okay. So it changes from 7.5. First, it is constant. Okay, the rate of change, the magnetic field is not changing. If the magnetic field is not changing, the EMF will not be induced. So up to 0.1, there will be a flat line. And in every region where there is a straight line, where there is actually no change in magnetic field, there will be a straight line. So I'm drawing this roughly. You can count the number of boxes and do this precisely. So up to this point, and then just in front of, I think 0.4 up to here, up to this point, up to this point. These will be flat lines. There will be no EMF generated because there is no change. Even though there is a value, it's not changing. So from this region to this region, we realize that the value is changing from 7.5 and it's coming back to 0. This is exactly the same formula that we solved in the previous question. The time frame was given to us as 0.15, which is given in this situation as well. So what will be the value of induced EMF? The induced EMF in the previous part was found to be 3.6. Right? So let's make a graph up to 3.6 by counting number of boxes and draw a flat line in this region. So this value is 3.6. Now we move to the next part. In this part, we see that the change is still the same. You see, this is still 7.5. So if I put the value of 7.5 in my formula of BAN divided by T, I will again get 3.6 millivolts. But notice that this time, this is in negative. It does not matter. We'll get to that later. This will again cause an induced EMF, but notice what has happened to time. You see, previously the time was 0.15, but the same thing has happened. It has decreased from 0 to 7.5 in a time frame that you will find by counting the number of boxes as 0.075, which is somewhat half of the time of this one. So if you decrease the time, the EMF is going to increase. If you halve the time, the EMF will become doubled. Right? So if this was 3.6, the next pulse will go up to 7.2, which is twice of 3.6, because the inverse proportionality. Simple as that. You divide this by 2, you get this by multiplied by 2. Now, why is the EMF positive? This is where the negative sign actually comes into play. Please pay attention to this one. You see, there is a negative sign. So whatever I do over here, the opposite will happen for this one. Now, right now, I can see that the gradient in this section, the gradient is negative. So my EMF will be positive. Why? Because the formula has a negative sign. So EMF is proportional to negative of change of flux. If I put it in negative gradient, negative multipliers gives me a positive answer. If I put in a positive answer, multiplied by negative gives me a negative answer. So anything to show this opposition. So since in both cases the gradient is negative, the pulse of the EMF is positive. In this question, he talks about Faraday's law of electromagnetic induction, and this is basic definition of O levels, that the induced EMF is proportional to rate of change of flux or magnetic flux. Now, notice that this question is about introducing magnetic field from one coil to another. You see, there is this coil, the coil with larger gaps, and then we have another coil that is with the smaller gaps, this one. Okay, so they are both wound on a single core. I current is because of the larger solenoid, and C will experience an induced EMF over here as well, because if you provide changing current, it causes changing magnetic field, and if a conductor experiences changing magnetic field, it will produce an induced EMF. That is how transformers work. So he tells you, he gives you these values. You can pause the video, read the question for yourself. He says that we want to show that the magnetic flux linkage, so that means he's talking about phi L equals to NAB, is going to be this much. Now, one interesting way to solve the question is, that even during examination, if you're unable to get this answer, that means that you're putting some variable wrong. Okay, so let's try to, I'm going to show the method that is interesting in this way. So phi L is equal to NAB. So the number of turns are very simple. They are 85. The cross-sectional area found previously as pi r square is 3.2. So this will become 1.6 centimeters whole square into B, the magnetic flux, which is given by this formula. Since it has a pi, I will write this down as 3.14 into 10 to the power minus 3 and into I, which is the current already given over here. So this is 2.8. Let's say that you put in these values and you don't get your answer. You don't get 6 power minus 4. Recheck your calculation first. If you still get the same answer, then put the answer over here, 6 into 10 to the power minus 4, and find out which variable you were confused about. What value is he putting over here so that he gets this answer? I'm sure that there is always going to be one variable that you're unable to figure out. So reverse engineer the problem. And whatever variable comes out, try to find it in the question where does it exist. So let's say some student gets confused about the cross-sectional area. You will get 1.6 minus 2 at the end of the reverse engineering solution. You can quickly come here that if this is cross-sectional area, has he doubled it or has he halved it? What is he trying to do? Then it may click to you in the examination or during practice at home as well, that this is how you solve the question. This is how you visualize it. Okay, so you can make your notes from the marking scheme as well. So when you solve this, the answer comes out to be 6.0 into 10 to the power minus 4 Webers, not Webers per meter square, because that is for B, magnetic flux density. It says the current is reversed and the solenoid is 0.3. What is the induced EMF? Now notice what is the meaning of reversed. It means that first, if the current is 2.8, it is now changed to negative 2.8 in a time frame considered from this point to this point in a time of 0.3. Now, when I write down the formula for induced EMF, I know that this is rate of change of magnetic flux with respect to time. I have calculated the flux in the previous part. That is why this question is for 2 marks, because I don't need to do that again. I know the flux, but I know the flux changing from 2.8 to 0, as he mentions in the question, that the current in the solenoid is 2.8 ampere, or it is increased from 0 to up to 2.8 amperes. That means it goes to 0. But now I have to go to negative 2.8. So what has happened to the variable of change? What has happened? It has changed twice, or you can say at least 2 times in the same amount of time, right? So let's multiply this flux with 2 instead of just keeping the flux as it is. So flux is here. I multiply this with 2 because of the reverse polarity, because of this graph change is from 2.8 to minus 2.8, and then divide this with 0.3 seconds of your time. You will get an answer of 4 milliseconds, 4 millivolts. So this is 4.0 millivolts. Now this will be used in the next part of the graphic analysis. This is where the question is going to get. Now notice that over here we have current. In the previous question we had flux density. So as I explained earlier, it does not matter. They're exactly the same things. The process will take place in exactly the same way. Okay, let's do that. So it says to draw the graph of induced EMF, and we know that it is equal to the rate of change of flux. And the flux is actually proportional to the current, and the gradient of this function will tell me about the induced EMF. So it changes from 2.8 to negative 2.8. Okay, all right. In this region, the induced EMF. Now, first, very simple. First, let's draw those regions in which there will be no magnetic field. Sorry, there will be no induced EMF in these regions. Okay, because the current is not changing. So from 0 to 0 point something at this point, the graph will remain 0. And from 0.6 to 1.0, from 0.6 to 1.0, the graph again remains 0. No voltage, no change in flux. And from 1.6 onwards, again, the voltage is 0. So wherever you see a flat line, wherever the gradient is 0, wherever there is no change, there will be induced EMF of 0 volts. Now it changes from a 2.8 to negative 2.8 in a time frame that starts from this end and ends at this point. Now this time is actually given to us as 0.3 seconds. So you can check this with the graph boxes as well. So in the first pulse that we see is going to be up to 4 millivolts. So let's say that this is up to 4 millivolts. Notice that the gradient is negative. That's why I'm drawing the EMF to be positive. Okay. Next thing, the gradient is positive. So the EMF is going to be in the negative region, but let's see how high is it going to go. If you have counted the number of boxes and you've taken this as 4 and 2, then this will be -2, and let's say this will be -4. In the second region, the change is still from -2.8 up to a positive value of 2.8. But notice what has happened with time. The time frame is actually lasting from 1.0 to 1.6, which means that this time the time is 0.6. And this is how the examiner will sometimes try to ask the question. Now 0.3 and 0.6, it is 2 times higher time, 2 times larger time. So how we have visualized EMF, that is rate of change of flux with respect to time. If you increase time, the induced EMF decreases. Now we have doubled the time. If we double the time, the EMF reduces by 2. So in this pulse, there will be a negative EMF, but up to only 2 millivolts. This was up to 4 millivolts. These questions are going to be about eddy current, so please pay attention. First, I'm going to write down the answers and then I'm going to discuss them. He says that the temperature of the core rises. Why is that so? Why does the temperature of the core rises? It's an insulated wire. It's not even in contact. What's wrong with it? Why is there a current in the coil? In the core. So what we are going to say over here is that the current in the coil will, since this is a copper core, it is a conductor. A conductor experiencing a changing magnetic field will experience an induced EMF from Faraday's law. So we will say that the coil has alternating current leading to changing magnetic flux. This changing flux in the, or sorry, you can say experienced by the core will cause an induced EMF in the core. This causes induced current in the copper core. Current through the resistance of the core produces a heating effect. And these currents are called eddy currents. I've discussed this in the transformers video of A levels as well. So what's actually happening at this point? What did happen? This will be common for the rest of the parts as well. So we are passing the alternating current. The magnetic field is sometimes becoming north and south, sometimes it's becoming south and north. Now when we change the magnetic field for any conductor, be advised that if this had been a plastic core, it wouldn't matter. This is a copper core, it's a conductor. It could have been iron as well. Iron will also experience the same phenomena. Now we discovered in Faraday law that if you provide a changing magnetic field to a conductor, it will experience an induced EMF. Now this copper core is experiencing a changing magnetic field on the outside, which is provided by the coil wound on it. Now this induced EMF will be caused on the copper core, and let's say that this is positive terminal of the battery, because induced EMF is voltage, and let's say this becomes the negative end of the core. So the current starts flowing from positive to negative, and in the next moment when the current direction changes, for example, then of course the south and north pole also change, and it's possible that this becomes negative and this becomes positive. So the current starts going back again. So what's happening? As the current in the coil is changing at all times, because it's an alternating supply, the current is changing at all times. The current keeps moving from right to left and left to right. And if the current is moving through a resistor, then it's going to produce a heating effect due to the P equals to I square R formula. There is current, there is a resistance of the copper coil, and it is going to cause heating of the core, which is made of copper. And this current that is being generated is actually called eddy currents, because we did not intend them to be produced. We were not looking for them. We were not trying to make them, but they are there nonetheless. We can't avoid them. In the transformers we can. We have a method to avoid this. You'll have to see that video how we do that. And this is another very interesting common question, and it is very much asked in interview questions as well. If you go for a job, they will ask you this question, if it is a science job. I have heard this question from students coming back, reporting for internships, reporting for other things, that this question is asked from them if they're going for a STEM internship, right? So there is a plastic tube, there is an aluminum tube. Who's going to fall first, magnet A or magnet B? Take a moment to think about it. Magnet A will fall first and magnet B will fall later. Very peculiar behavior because everything else is same. The mass of the magnet, the size of the magnet, the size of the tube, every single dimension is same. Then why there is a delay? You see, when the magnet falls through the plastic tube, it just falls through the plastic tube. It has nothing to do with it. It has nothing to do with the plastic tube. It will not interact with it. But when it passes through this aluminum tube, now aluminum is a conductor. When the magnet passes through it, the magnetic field that is around the magnet is actually cutting the core itself as it is moving along. So we can say that there is actually a changing magnetic field with respect to time in this conductor. Now, when the conductor experiences the changing magnetic field, what's going to happen? It will produce an induced EMF. Although these magnetic field lines are cutting the conductor as it is moving down, there is now an induced EMF. Let's say that this is an induced EMF. Now, this will start causing the flow of current in this direction. Now, we know that when current starts flowing, it has its own magnetic field that is in the circular direction that we have done in the chapter of F equals to ILB, force on a current carrying wire. This magnetic field, which is now being produced because the magnet started moving, will oppose the magnetic field of the magnet itself. A manifestation of Lenz's law, that if the magnet had not started moving, would this current exist? No. So, opposition of the maker. So the magnet started moving, there will be an induced EMF in the aluminum itself. That induced EMF is going to produce such a magnetic field that is going to oppose the magnetic field of the magnet that started moving. So that is why this opposition will cause this magnet to actually fall with a delay. This will slow down through the pipe and then fall immediately to the ground because now it has exited the pipe. So this will be later and magnet A will be fall sooner. This is the answer he's expecting. That is, write this down over here in your own words. There are two ways you could have written this down. One is the energy method and one is the magnetic field method. The starting point is exactly the same for all of them. So moving magnet through the aluminum core causes induced EMF, right, giving rise to the induced current. Now this is where it gets separate. So let's say we call this point number 3. I will cover 3 and 4 in the same point, but this is the rest of the answer. So giving rise to the induced current. This current creates an opposing magnetic field that requires work done so that the magnet can move along. Okay, so this will remove the energy. What he's trying to say is that if the magnetic field is opposing the magnet, then the magnet has to force its way through the tube. It will have to use some energy. And what energy does it have? If it's coming from a height, it's gravitational potential energy, which is going to convert into that. Another way to look at this would be to involve eddy currents. This is the method, this is the idea that I prefer, so that it forces you to remember eddy currents concept. Please don't forget about it. So first 2 points are exactly going to be the same, but we're going to change the answer at this point. So giving rise to an induced current, this causes eddy currents in the pipe. This current produces such a magnetic field that it opposes the movement of the magnet itself, ultimately slowing it down, as I've explained in the theory as well. Okay, all right. And if you're thinking about the question being of 5 marks, I've covered at least 2 points in a single point, which is point number 1 and 2. Okay, so these are actually qualifier for 3 marks. Then you have to give the details. Either you can do in terms of work and energy, or that you can talk about the eddy current concept. Okay, let's move to this part. He says that moving the magnet causes the resistor to heat up. Very easy. Faraday's law, involve Faraday's law in this. This is a very simple concept, included this question so that you can develop a theoretical answer for this question. So what will you write down? The motion of the magnet causes a change of magnetic flux leading to an induced EMF on the coil. Now, when the coil has an induced EMF, plus and minus, it will cause rise to the induced current. So first you talk about the induced EMF, then you will talk about the induced current. Now, when there is an induced current in the coil, what will happen? We know that current through a resistor of value R produces heating effect, right? So 1, 2, 3, and you will mention P equals to I square R, the power loss due to this formula. Plus, what will be the fourth point? The fourth point is actually about the effort. Okay, so he says where this thermal energy is actually coming from. We understand that the current is going to produce the thermal energy effect. It's going to heat it up. But where did it actually originate from? This actually originated from the work done in order to push the magnet into the coil. Why is it going to require an effort? Because when we provide this current, the current in the coil produces such a magnetic field which starts opposing this movement of the magnet. Lenz's law. So according to Lenz's law, since there is going to be an opposition, whatever opposing force there is, we need to provide at least that much force so that we can push it in. That's why the origin of this thermal energy is going to be the work done to push the magnet inside the coil. Of course, if you have writing space, you can mention about the Lenz's law opposition. Okay, why there is a force opposing the movement of the magnet. Then he says how the transformers, now this is a very repeated question as well, why the transformer's primary current is not in phase with the induced secondary coil. He says that if, for example, we provide this current to the primary coil, primary input, this is the transformer, let's say, this is the primary side, this is the secondary side. He says that if you provide this voltage in the primary current or in the primary side, the output current is actually going to look like this. If this is a sine function, this is a cosine function. Why is that? Why are they out of phase? You see, the current, for example, we're going to look at the current because current can be proportional to the flux, right? So if the flux is changing like this, the induced EMF is actually the gradient function of the flux, which we used to solve the questions of the graphical analysis over here. Yes, in these questions, we'll be looking at the gradient, right? So what's going to happen? We're going to say that when the gradient was maximum, our EMF was maximum. When the gradient became constant, our EMF became zero. When the gradient became negative high value, our EMF attained a negative high value. Okay. And when it became constant, our EMF became zero again. When it became high again, we attained a high value. So this graph is actually the gradient function or the gradient of this graph. That is why it is out of phase. And no matter what polarity you provide, you're going to get the answer in the opposite way, at least 90 degrees out of phase. Okay. I hope that I've explained the theory. You can go and check this question out and marking scheme as well. This is May, June 2015, paper 4.2 and question number 7, part B. I've discussed it with you. You can look at the marking scheme and just memorize it, that there is always going to be a 90 degree out of phase. And why is that? Because this is made looking at the gradient.